So today I'm going to talk to you about the application of ontologies and ontology engineering to the humanities. Of course, this is a fairly new topic, but I hope that I can show that it's an exciting one and one that holds a lot of promise for the many different disciplines within the big tent. In some ways, of course, the use of ontologies has already started to gain ground, especially, for instance, in the cultural heritage domain, to the point where it's now starting to become, I've noticed it's starting to become a buzzword in the field, in the same way that it's been a buzzword for a few years now in other disciplines. So I'm hoping to do two things with the lesson this morning. The first is to give you a good grounding in the basics of ontologies. And so the first part of the lesson is going to be a gentle, but I think reasonably comprehensive introduction to the field, within the given time limits of that I'm under this morning. And the second thing I want to do is to look at the application of ontologies to the digital humanities and look in detail at a number of specific cases. So the second part of my presentation will focus on that. Okay, so without any further ado, let's move on to the first part. And I've tried to make this as gentle as possible, but obviously I'm only going to be able to skim the surface of lots of different ontology-related topics, so I can't really go into as much depth as I'd like. But if you're interested in any of the things that I mention, I'd be happy to give you further pointers, and I can give you other further references. So if something's not clear, or if you're interested in something that I spend very little time on, then please contact me. So as you probably all know, the word ontology has already had an established meaning within the field of philosophy before it ever came to be used within the context of computer science. In philosophy, of course, it refers to the study of being, of that which exists. We're going to be looking exclusively at the use of the term in informatics. And the use of the term in informatics or computer science is not entirely unrelated to the use of the term ontology in philosophy. And it's actually a very interesting topic for discussion in its own right, but I'm not going to discuss it today. I spoke just now about the use of the word as a technical term in informatics, and you may have heard it being used in that sense in various different contexts without knowing exactly what it meant. Maybe you kind of worked out that it's something like a taxonomy. It's a way of classifying a domain, and that's not too far off the truth, because even if it's a little too narrow. You might also know that ontologies usually describe a domain from the point of view of a certain community or a discipline. That is, they help to organize domain knowledge. At the same time, though, an ontology is something that's written in a formal language, and it's actually a computational artifact. It's something that you can save as a file on your computer. So all of these are different aspects of the definition of the word that maybe you kind of vaguely knew about before, and these will actually lead you to the definition of the word as it is generally understood in computer science. So let me take a gulp of water. So one of the most popular definitions of the term, the one that's probably most cited, was given by Studer et al. In 1998, and it's a fairly simple definition. It doesn't really assume any specific technical or implementation details. It just says that an ontology is a formal, explicit specification of a shared conceptualization. So let's try and break that down. Formal here means that ontologies are described in formal languages that have a clearly defined syntax and semantics. Explicit means that we really want to make our assumptions clear and explicit and as unambiguous as possible. And shared means, as I kind of alluded to in the last slide, that it's really the product of a community effort, or that it describes how concepts are used within a particular community. Now, that definition is probably much too simple to describe how the term is actually generally used, tends to be used today. So it's, in addition, I think it's important to also emphasize that ontologies are usually composed of classes, of the classes and individuals of interest in a domain, along with the relationships that hold between them. And in fact, as I will go on to describe in a little bit more depth later on, you can usually represent an ontology as a graph structure. So when you create an ontology, what you're really doing is you're trying to make explicit the shared assumptions that hold in a given community, and also you want to end up with a resource that makes these assumptions machine actionable up to a certain extent, of course, and there are limitations based on how expressive the languages in question actually are. And again, this is something that I'm going to be discussing further in my presentation. So I've given you a bit of a hint about what ontologies actually are. So now I want to actually talk about how they're used in practice. So in many cases, they're used to define terms in a controlled vocabulary, where you can use an ontology to give a clear and formal description of a concept that's used in a domain. And then you can also do other things like, for each concept, you can add the different labels that concept has been given in different languages. You don't necessarily need an ontology to do this, and there exists other kinds of other ways of doing it. For example, by using the Scots model, and we'll look at Scots as well later. But what ontologies give us is a lot of expressivity and a lot of flexibility, and also the possibility of actually running reasoners on the ontologies and deriving new knowledge. So, in order to probe a little bit further into how ontologies are used in practice, I want to single out one domain of research in particular, and that is the biomedical sciences. Ontologies have had, it's probably the domain in which ontologies have had the greatest success and made the greatest difference to the field. To the extent they've really become part of the everyday practice of researchers in the biomedical sciences. And this has meant also that there exists a wide variety of tools and resources for the biomedical sciences, especially when you're talking about the tools that have been developed in that domain. In theory, many of these can actually be readapted for work in other domains, and I would claim also for the digital humanities. So, to go into a little bit more detail as to what ontologies are used for within the biomedical sciences. So I would say that there are four main uses of ontologies. I can group them into four different areas. So the first use of ontologies is really, and I think probably it was originally the primary use, was the annotation of data sets with standard identifiers. And this was a way of basically enabling the querying of multiple data sets that came from different institutions, that came from different projects. So, for example, one of them, probably one of the most important such ontologies that was used for annotation is called the gene ontology, and that was actually really, really famous within. That's actually a really kind of well-known ontology within the field of ontology design because of its use and its popularity. So another use of ontologies in the biomedical sciences is in order to provide vocabularies for applications that rely on domain-specific terms. And for example, this could mean, for example, text mining using ontology labels. And then there's also the possibility for reasoning over ontology annotated data sets. And this has also had a reasonable measure of success, for example, in determining protein families. Then finally, there's also the use of ontologies as background knowledge for data mining and analysis. And as I go further into my presentation, you're going to see where, these kinds of uses of ontologies are really not, they can be really generalized, and they can be actually introduced into other fields, and hopefully, as I say, also into the digital humanities. And another field in which ontologies have had a big impact is in computational linguistics and in natural language processing, where they're used frequently in such tasks as word sense disambiguation and named entity recognition. And they're really looked upon as repositories of semantic knowledge. And in this regard, it's interesting to note that many people regard famous resources such as, well-known resources such as WordNet, VerbNet, and FrameNet as ontologies, since they contain both language-dependent and language-independent knowledge. I mean, this is arguable, but I think it's generally regarded to be the case that, especially WordNet, that WordNet is an ontology. Although, I don't think there's any hard and fast rule about what counts as an ontology and what doesn't. So this is still up for debate. This is something that I myself am working on. It's the use of ontologies to enrich computational lexicons with semantic information. For example, we can use ontologies to track the changes of meanings in words, or compare how different languages treat different concepts. And ontologies can also help to link lexicons together with corpora as well. But I'm not really going to talk about this. But it's something that I myself am actually working on in Pisa. In the digital humanities, we're beginning to see an increased emphasis on ontologies for the purposes of annotation and data integration. And I'm going to go into more depth on this in the second part of the presentation. But as I said, first of all, I want to actually get down to the nuts and bolts and to actually give you a kind of a brief introduction, reasonably brief, as to what ontologies are actually made out of. So, some more water. So, the first thing to emphasize is that ontologies, or at least the ones we're going to look at, are made up of classes, properties or relations, and individuals. And so we can usually think of an ontology as consisting of three separate components. The first of these is called a T-box, also known as the terminological component. Then there's the A-box, the assertion component, and sometimes there's also a separate R-box, which is the role or relation component. All of these things are described in a formal language, and so as I mentioned before, we can actually run automated reasoners over ontologies and then derive new facts from the knowledge that's already contained in the ontology. And there are various different kinds of formalisms or notations which we can use to construct ontologies, including even visual or graphic notations. But by far the most common kind of formalism for constructing ontologies is formal logic, and in particular a family of logics called the description logics. OWL, which is probably many of you have heard of, is is currently the single most popular ontology language in use. Is also based on description logic, and I'm going to go into detail in the relation between OWL and description logics later. So to give you a kind of a brief introduction to description logics. Really, the idea with description logics is to construct complex concepts from more simple atomic concepts using different kinds of operators. So sentences in description logics are made up of these concepts, which you can also refer to as classes, roles and individuals. And as I said before, we can create complex concepts from basic ones using the following operators. So these include the Boolean operators, intersection, union, and complement, the restricted quantifiers for all and exists, and the counting quantifiers, which is less than n, less than or equal to n, and greater than or equal to n. And we can also form axioms using the following operators, concept inclusion and equivalence. So if this is all kind of a little bit confusing to you now, I'm going to go through some examples just to make things clear. So, for example, say that we had the basic atomic concepts of human and male. Then, using the intersection operator, we can create the concept man by taking the class of all humans and the class of all males and looking at the intersection of these two classes. We can also create a concept that refers to parents, so the class of parents, by taking the union of mother, the class of all mothers, and the union of the class of all fathers. We can also, for example, create a class which refers to the class of people who have more than one child by using the quantifier that I referred to, mentioned on the last slide. So in this case, this complex concept is actually made up of the quantifier greater than or equal to 1 and the property has child, and the meaning of it is the class of all people or the class of all entities that have more than one child. And for example, if we now move on to the quantifiers, then we can create classes. We can construct classes such as the following. So in this instance, we use the for all quantifier with the has child property and the pianist class to create the concept, the class of all people, all of whose children are pianists. And then in the other example, we use the exists quantifier with the has child property and the class of archaeologist, but with the negation in front of it, to create the class of people who have at least one child who isn't an archaeologist. And also note that we can use the top and bottom as the most inclusive and most the inconsistent concept, respectively. So we can use the concept inclusion and equivalence operators that we saw a couple of slides ago to form axioms. And these axioms are ways of relating together different concepts, or if you like, to give ways of giving simple labels to complex concepts that are made up of lots of different more basic concepts. So, for example, we can in our T box we can actually state that the class man is equivalent to the intersection of the class of humans and the class of males. The class father is equivalent to the class of all entities that have more than one child. The class parent is equivalent to the union of the class of mothers and the class of fathers. And then, as regards the concept inclusion operator, we can, for example, relate together the class you with the class sheep by with the concept inclusion operator to state that the class of ewes is a subclass of the class of sheep. And then finally, we use the inconsistent, the bottom concept. This basically, you can think of it as referring to the empty set. So you can say that the class of male, the union of class of males and class of females is greater than the empty set, which is kind of a redundant thing to say, but there you go. Greater than or equal to the empty set. And as I've said, we can a set of such axioms goes under the name within the concept within the ontology domain. It goes under the name of a T box, and that's really the T box is the part of our ontology where we describe the different relations between the classes in the domain. We can also make assertions by combining concepts with individuals. So, as I said before, in an ontology, you have classes, properties, and individuals. And so we can relate together concepts with individuals. And in this case, for example, if we make the assertion, man, Donald, in this kind of this kind of this bracket notation here basically means that Donald belongs to the class of man. And then in the second instance here, we have that Melania belongs to the class of woman. And then we have an example of property which relates together two individuals. So in this case, Donald has child Baron. And in the last example here in green, we have that Baron has parent Melania. Now, similarly to the T box, which gave us which was made up of a set of axioms describing the relationships between different classes, a set of assertions like as I've kind of shown above is called an A box, and this is the part of an ontology which contains concrete facts about how the world is. And then finally, we would like to specify properties. This should be properties or roles. So, for example, we want to. No, this is actually right. So we want to specify different kinds of properties that maybe roles should have. So if we have the role has child, then what we want is that it should be the inverse of the role has parent. So, for example, if you have has child Donald Baron, then we want to be able to automatically derive the fact that or the assertion that Baron has parent Donald. And there are other useful properties that we would like to specify of roles, such as, for example, that the fact that the assertion, if we have the assertion that Donald has spouse Donald Melania, then we want that to be symmetric. So we want to also be able to derive the fact that Melania has as spouse Donald. We would also like to have the property of transitivity. So in this case, for example, if we have the assertion in our A box that Ivanka has Donald Jr. as sibling, and Donald Jr. has Eric as sibling, then we want to be able to derive the fact, the assertion that Ivanka has Eric as a sibling. And these properties of roles can all be specified in using additional operators, and these all go in the R box. Okay, so where is it? So I've just given you kind of a very brief overview of some of the operators that are actually used to put together concepts and roles and then specify the different kinds of properties that they can have. So description logics are really a family of logics that are kind of structured or that are arranged on the basis of the kinds of operators and axioms that they contain. So these operators are kind of you don't always find every one of these operators in a given description logic, and the less operators you have, the easier it is to work, or computationally speaking, the easier it is to work with a logic. And two of the simplest kind of well-known description logics are the logic EL, which contains just the concept operators intersection, negation, and exists, and the concept axiom, concept inclusion, and equivalent, but it doesn't have any role operators or axioms. I think that's a mistake. And then there's a logic ALC, which extends EL with the operators into union and for all. I think that's actually a mistake. There shouldn't be the equivalence sign there. And then letters are used to indicate each of these features and name the logics that result from adopting them. So, for example, the letter S stands for ALC extended with transitivity axioms. Now, as I mentioned before, different logical features have different computational costs in terms of how many computational resources they take up, or in the worst case, even whether they stop at all. And it's important to take this into consideration because, after all, one of the benefits of working with ontologies is that we can run automated reasoners over them, both to check for consistency and also to derive new statements. And as is so often the case, there is a fundamental trade-off to be made between the expressivity of a language and the computational efficiency of the algorithms for that language. And so I think this is a very nice diagram that gives you a kind of an idea of the kind of arrangement in which you can put different description logics. And as you see there, they're all given, they all have these names that are kind of based on series of letters, which tell you which of the operators and which different features each of these logics actually contain. And very briefly, just to say that the semantics of the description logics is fairly straightforward. And just to say that it's actually very similar to first order logic, and that means that they're kind of straightforward to work with, since we've been studying first order logic for around 130 years now. So now I'm going to move on to ontologies in the semantic web. So here on this diagram, I've put the so-called Semantic Web Stack, which is a representation of the different technologies and standards that go together to make up the semantic web. And as you can see, that OWL is actually inscribed on the side of one of the blocks here, so you can't really see very well, along with RDFS and OWL and Scots, and it's really OWL that's going to be the focus of this section. But I'm going to lead up to it by looking at RDFS, and also Scots. So ontologies in the semantic web seem to go together particularly well, and this is to do with the fact that, as I said, that typically ontologies are really descriptions of graphs. So the different classes in an ontology can be seen as nodes, and the subsumption and other relations used to including equivalence relations used to label them can be seen as labels of the edges between these nodes. And so the RDF meta model is an appropriate framework for representing ontologies. And additionally, each resource in an RDF triple has a unique identifier. And as you've seen, this is important for several of the applications of ontologies as controlled vocabularies or in annotation. And it's also interesting to note that the definition of ontologies as shared conceptualizations is consistent with the emphasis on the use of shared standards and the interlinking of data sets that's really at the core of the semantic web and linked open data. So as we've said, RDF is a good foundation for building ontologies. The RDF meta model already stipulates that data be set down in the form of subject, predicate, object triples, where the subject and predicate are resources that are identified by a uniform resource identifier, or URI or URI, and the object can either be a resource identified by a URI or a data value. RDF already gives us the RDF type properties so that we can make kind of simple statements relating individuals to classes, the kinds of statements that you saw in the A box, in the assertion box, in the description logic slides. So for example, here I've taken this example from DBpedia. Basically says that Mariano Rajoy belongs to the class office holder. So that's already a nice step towards being able to represent ontologies, but obviously it's not enough. We don't have enough expressivity. And an extra step in the right direction is given by RDF scheme, or RDFS, which allows us to encode subclass or subsumption relations between classes. It also gives us a subproperty of relations so that we can actually create hierarchies of properties. And we're also able to define the domain and the range of a relation. So, for example, with the subclass of relation, we can say that office holder is a subclass of person, and then we're able to derive using basic description logic that Rajoy is a person, belongs to the class person, from the fact that he's an office holder. And also, for example, we can, with the ability to define the domain and range of a relation, we can specify, for instance, that the property employer has a domain person and has a range organization. So this means that if you have an example, an instance of employer that relates together two individuals, we can assume that the subject of employer is a person, and we can assume also, and we can derive the fact that the object of the relation is an organization. We can do this automatically. Before I actually move on to talk about OWL itself, I just want to mention Scots. And if you only really want to construct a taxonomy or a thesaurus, and you might not necessarily need to go down the OWL route. In fact, there's a nice lightweight alternative to OWL, which is the simple knowledge organization system, which is SCOS. And SCOS is really concept-centric, and you get kind of basic model in which you can attach labels, terms terms as labels to concepts, and concepts can then be arranged in hierarchies using the broader and narrower properties, or associated together using the related properties. And just also want to point out that there exists a lot of tools for editing or managing SCOS datasets, including several tools which are also used in addition for working with OWL ontologies as well. So now we finally get to OWL, or the web OWL ontology, and there's a link on the OWL page, Wikipedia page, if you want to know why it's called OWL and not WAL, since it actually stands for Web Ontology Language. OWL, again, is in fact a family of knowledge representation ontology languages rather than a single language. And like a lot of other important things nowadays, it was based on work originally funded by DARPA. So OWL comes, so there are at least 3 different flavors of OWL, based on the level of expressivity that you require. So the simplest kind of version of OWL is called OWL Lite, and it's really intended for creating lightweight ontologies such as classification hierarchies, and it's much easier to work with. It's much easier to provide tool support for. But as I said, it's maybe not expressive enough for a lot of things. So then you get the next level of expressivity, which is OWL-DL, which is said to boast the maximum level of expressivity without incurring certain nasty computational properties such as undecidability, which means that you can't be sure that the reasoner will ever end, that there's no guarantee that it won't go on forever. DL in this case stands for description logic, and interestingly enough, both OWL Lite and OWL DL correspond or equivalent to 2 different description logics, which are shift D and join D. Again, they're referred to in terms of this kind of string of letters. Again, reasoners for OWL D tend to be slower than those for OWL Lite. And then finally, there's OWL Full, which is most expressive of the 3, but it lacks certain computational guarantees and it's not decidable. So depends on what you want to do. But there are certain use cases where you might want to actually take advantage of the full expressive power of OWL Full rather than using the first 2. So again, OWL builds on top of RDF and RDFS. So what are some of the new features that OWL offers us over and above the features of RDF and RDFS? Well, first of all, OWL allows us to add constraints to the definition of classes and properties that correspond to the features of the description logics that we looked at earlier. And I'll go into more detail I think in the next slide. But it also gives us a number of very useful properties. OWL gives us the property same as, which enables us to specify that 2 individuals are the same, and also the different from property. So, and I've taken these 2 examples from DBpedia. So here we have the DBpedia resource, I think in English DBpedia, referring to Leonardo da Vinci. And I can specify that this is the same as, it's the same, referring to the same entity, referring to the same thing as the DBpedia Japan entry for Leonardo da Vinci, which obviously written in Japanese. And then I can also say that, for example, the DBpedia entry Leonardo da Vinci, da Vinci all in one word, is different from the DBpedia entry for Leonardo da Vinci, the artist. In the first case, it's actually a butterfly called Leonardo da Vinci. So again, these are two very useful properties that you've come across a lot when you look at linked open data sets. And also you have the equivalent class property as well. So OWL allows us to specify two different kinds of properties. So the first of these are the object properties, which are binary relations which hold between instances of classes. So for example, the property country, which basically stands for A is in the country of, only holds between instances of classes. So here we have Madrid, which is an instance of city, and Spain, which is an instance of country. And then you have data type properties, which are, again, binary relations, but this time they hold between class instances and RDF literals or XML schema data types. So, for example, the name property, which basically you can read as A has the name B, holds between, in this case, the city Madrid and the string Madrid in English. And then in the next example, we have population total, which holds between an instance of a class, in this case Madrid, and a non-negative integer, an XML schema data type non-negative integer. So with OWL we can specify transitivity and symmetry of properties, and we can also ensure that, for instance, that the properties or roles are functional. So, for example, if you look at the population total property again, you don't want a country to have, or city or country or any location to have more than one population total. So in this case, if you have two different triples where Madrid is the subject of each of them and population total is the predicate, then you can assume that basically the object of the property is the same. And something similar is the case, but in reverse for properties like is father of. And we can also, with OWL, we can also specify that one property is the inverse of another. So, for example, we can make sure that has father is the inverse of the property is father of. And again, OWL allows us to encode the sort of property restrictions that we saw in the previous section on description logics. So all values from encodes for all, and some values from encodes exists. And then again, we can use cardinality, max cardinality and min cardinality to encode the quantifiers that we saw earlier. And the great thing about OWL is that there exists a lot of tools for working with OWL ontologies. There exists lots of numerous reasoners, and the most well-known of these are FACT, Hermit, Pellet, and Racer, and as well as ontology editors such as Neon Toolkit and TopRaid, which is actually a commercial product, and a Fluent editor. And a lot of these are actually open source and free. But to date, the most popular tool for OWL is Stanford University's Protege, which is a free open source ontology editor. I was going to do a demo, but probably don't have enough time because I think I used to have 2 hours, but I only have an hour and a half. So you can just download Protege. It's actually really easy to use. And I would recommend you look up I put a link, but there's a famous pizza ontology tutorial, which everyone basically, it's the go-to tutorial if you're wanting to learn how to use Protege, and also to learn a little bit about OWL as well. We've talked a little bit about the features of OWL and looked briefly at I wasn't able to give a demo of Protege, but I would recommend if you're interested in working with OWL and you don't want to work with the source files, to use that because it gives you a really nice graphical interface. But now I want to talk about some of the ontological resources that are available on the Semantic Web. Here, by the way, is the latest version of the Linked Open Data Cloud. And the first resource I'm going to talk about is probably, I think, one of the more popular of the resources on the cloud, and it's actually one that I've already mentioned. So, DBpedia. And DBpedia is probably the most extensive ontological resource available at the moment on the linked open data cloud, as well as being one of the most well-known and amongst the most linked to nodes in the open data cloud. And as the name suggests, it's actually it's really an attempt at converting information from Wikipedia. So it's actually an RDF version of Wikipedia. And yeah, it's generally considered to be, and it's used as an ontology, and it's made use of in countless different applications, and especially in NLP. DBpedia can be accessed via a Sparkle endpoint. And there's also a tool that's available called DBpedia Spotlight, which is also available as a web service, an application that automatically annotates text with DBpedia links. And there's a demo that I think I put the link on the slides. It's really kind of interesting to work with and enter different texts and see what it comes out with. So, aside from DBpedia, there are several other fairly well-known semantic web ontologies that are on the linked open data cloud that can be downloaded and queried. I'm not sure if they can all be downloaded, actually, but they can all be queried. So the first of these is BabelNet, which is it's a kind of really extensive multilingual ontology that links together Wikipedia, WordNet, and a lot of other data sets. And it's become fairly kind of well known, at least within the field of natural language processing, because it's been used to achieve the state of the art for a lot of NLP tasks. And then there's Yago, which again is derived from Wikipedia, WordNet, and GeoNames, and kind of Yago's kind of unique selling point is that its accuracy has been manually evaluated. Then there's BaseKB, which is it's a linked data version of the Freebase dataset, which is interesting because it was used by Google, as well as probably still is, as one of the sources of their knowledge graph. There are also several other upper level ontologies, but we'll look at those in the next section. So let me. So before we go into the next part of the presentation, which I will look in more detail in the application of ontologies in the digital humanities, I want to spend a few minutes and a few slides to really touch on some of the issues involved in designing an ontology, and also for evaluating whether an ontology is well designed or not. And so I want to kind of sound a note of caution, because with the ontologies there's a real risk of producing something that looks kind of impressive and it seems to look good, but it's actually, because it's been badly designed, it's actually not very useful at all. And I think especially when it comes to working with ontologies, it's important to emphasize the old computer science saying, garbage in, garbage out. Again, logic and automated reasoning can be very powerful as tools, but poorly thought out premises will inevitably lead you to unsound results. And if you have an inconsistent theory, then you can prove literally anything. Just one first results that you learn in formal logic. So it's therefore important to kind of to pay attention and look at some of the guidelines and standards and best practices that have arisen within the domain of ontology engineering over the years. And so the first thing I want to mention is the distinction between the open and closed world assumptions. OWL and many other knowledge engineering languages make the open world assumption, and I think if you're working with ontologies in any capacity, it's important to know what it is. And it basically means that the failure to derive a statement from your ontology, or in general from your knowledge base, does not mean that you can assume it's false. So for example, if you're only able to derive one instance of the relation has-child with Donald as the subject, for example, has-child Donald Ivanka, this doesn't necessarily mean that Donald has only one child, unless we've made this explicit elsewhere in the ontology, and then perhaps you can derive it from using an automated reasoner. But if you can't assume that Donald has only one child. This is something that you can assume, for example, in certain programming languages and also in databases. So in databases, they make this assumption. So, for example, the famous example that they talk about is if you have a database with flights between different cities, if you can't derive if you query the database for a flight from between two cities and it doesn't exist, that means you can assume that there is no such flight between these two cities. So this is really an instance of the closed world assumption. But with OWL, we don't make this assumption, and therefore it's important to be explicit and to be as explicit as possible when you're trying to decide what you're going to put into your ontology and what you're going to exclude. So another important consideration when it comes to designing ontologies relates to the use of upper ontologies, and these are ontologies which consist of the most general organizing concepts, and these can be used as the highest layer in a domain ontology. And again, this is useful for two main reasons. And the first is that it encourages interoperability amongst ontologies. So if my ontology and your ontology are both structured using the same upper level concepts and properties, it's much easier to link them together. The second advantage is that it allows users to focus more on domain modeling rather than on really kind of basic questions about what is an event or what is an actor, because these are already dealt with in the upper level ontology. And amongst the most popular and well documented of these upper ontologies are Dolce, Sumo, and BFO, and lastly CDOC CRM. But we're going to look in more detail at this later on, because it's really, it's really, I think, one of the most successful uses or ontological resources within the digital humanities, and so I will go into some more depth on it. And then penultimately, when it comes to ontology design evaluation methodologies, there's only really one that kind of stands out, both for its philosophical rigor and for the fact that don't really exist too many other prominent ontology design methodologies. OntoClean is, as I said, it's kind of fairly philosophically rigorous, and it uses meta properties such as identity, unity, and rigidity, which are actually derived from work in metaphysics, and it uses these meta properties in order to evaluate the correctness of taxonomic relations between concepts, and to evaluate whether these are actually kind of spurious or not, or whether we need to introduce other kinds of relations into our ontology. Unfortunately, it can be kind of difficult for novices to follow, and it actually requires quite a bit of training to be able to implement. And actually, they've done experiments, found that inter-annotator agreement tends to be quite low with OntoClean. But actually, I still believe it's very important to study it, because it actually gives you a very good insight into some of the more common mistakes that people make when designing ontologies. So finally, in this section, I want to very briefly mention ontology design patterns, which are established and successful solutions to frequently occurring modeling problems. So you can really think of them as recipes for solving common issues or common problems in ontology design. They also tend to make ontologies more modular, and therefore, if you have a large ontology, it's much more manageable if you have the ontologies broken up into different modules. Happily, there's a wiki. Exists a wiki of ontology design patterns at the following link, and that contains patterns for modeling things such as sets, topics, social realities, even chess games. It also contains a list of exemplary ontologies, they call them, which you can refer to when you're creating your own ontological resource. So finally, we arrive at part 2. How much time I have? Okay. So far, we've looked at. We've looked at what ontologies are, what they're made of, how to design one, and very briefly we've looked at what they can be used for in areas such as biomedicine. But now we're going to return to our beloved digital humanities, and in the following slides, I'm going to look at a series of tools, resources, and case studies in order to understand perhaps how ontologies can be of use to humanists in carrying out their work. But I'm not going to be comprehensive, and there are things that I'm not going to be able to cover in the rest of the presentation. For instance, I'm not going to talk about specialist domain ontologies dealing with music, history, or archaeology. So bearing that in mind, let's continue. The first thing I want to talk about is CDOC CRM, which is an upper ontology. CDOC here refers to an international committee for documentation, which was instituted by the International Council of Museums. And CRM refers to conceptual reference model. CDOC CRM was originally created for the cultural heritage domain. So, for example, for data sets coming from museums or art galleries. And eventually it became successful and popular enough that it was eventually published as an ISO standard. The intention with CDOC CRM was really to create a resource that would mediate between different cultural heritage data sets, that would facilitate data integration and exchange. And it does this by making descriptions of objects more semantically transparent using concepts and properties from CDOC CRM itself. So, more precisely, the idea is to enhance dataset vocabularies semantically by aligning them to CDOC CRM, and then ensuring interoperability based on the meanings of the data. The ontology itself, the CDOC CRM ontology, consists of a number of real-world concepts linked together using properties. And the designers of CDOC CRM are kind of quite insistent on this link with the real world, because they claim that anchoring their ontology to reality is kind of puts a constraint on the kinds of entities and the kinds of things that you can actually put on in your ontology or in the ontology. And another thing to point out is that CDOC is a very event-centric ontology, so that really focuses, it has a real focus on events. So events which lead to the creation of an object, or events around its curation or its annotation. But generally it's organized to an upper level. It's organized in terms of things that persist through time and events which happen rather than are. So here there's a bird's eye view of the ontology, of the CDOC CRM ontology itself. I think one thing that's interesting to note here is that they made a separate class for appellations, which are titles used to identify resources. But for the rest, it's kind of fairly standard upper level ontology. I'm going to, don't know if you can see it very well, but I've taken it from a manual for aligning datasets to CDOC. It's actually a record from the British Museum for a Japanese sword. Probably can't see it very well, but it has different kind of dataset categories here. So, such as an internal ID, a description of the sword, details about its production, as well as metadata about when it was exhibited and its curation. And so what you can do with CDOC is you can actually map these categories to relevant CDOC concepts. And as I said before, it's very much an event-centric ontology. So, for example, you can group together several different categories here, relating to production, to inscription, to the event of authoring, to the class of events authoring, to exhibition, and to the class concept of acquisition. So this is by aligning your dataset, your categories to your dataset categories to CDOC, it basically helps to make your dataset much more interoperable and allows you to actually query across multiple different datasets. And as I said, I mentioned this in relation to biomedical, to the biomedical domain, and in that context, it's actually this idea of using ontologies for making datasets more interoperable has actually really been, hugely successful. And I think with CDOC CRM, you're starting to see something similar also within the cultural heritage domain. CDOC CRM has had a massive uptake within the cultural heritage community, and not just within the cultural heritage community. And actually, relatively recently, there's been an attempt to harmonize CDOC CRM with the functional requirements for bibliographic records data model, FRBR, and the name of the resulting resource is FRBR-OO. And this is the intention with this is to make it easier to share both library and museum data sets. And in addition, CDOC CRM has got several other modules that build on the success of the original core model, including there's a provenance model, there's a spatio-temporal model, as well as a model for archaeology and buildings, and there are several others as well. So talking about, in the last slide I mentioned the FRBR, and which is a model for bibliography. So another important ontological resource here, I think, is the SPAR ontology, the SPAR ontology suite. So this is not a single ontology, but it's actually a suite of ontology modules, which are kind of intended to help in the creation of machine-readable RDF metadata, and for every aspect. So basically, they have in mind every aspect of semantic publishing and referencing, and so SPAR gives you a host of ontologies which enable you to kind of create semantically rich metadata for describing published text. It also contain one of these ontology modules is actually a bibliographic module that's actually aligned with the FRBR, and so the SPAR ontologies allow you to do several things, amongst which, for example, you can specify citation links, you can specify also the roles and contributions of different authors, and you can also describe, for instance, the structure of an article. And there's several other things, and I would direct you to the SPAR webpage, and it's actually really well designed and well structured as well. And I think it's really the measure, I think, as with CDOC, the success of SPAR can really be measured to a great extent by the uptake that it's had, and the different data sets that it's been used. It's been used in to help model. So, for example, it's been used in by Europeana, by SiteUlike, by data.open.ac.uk, and also by the Nature Ontology and the Semantic Lancet, amongst many other different data sets. And then before I move on to the next topic, I just want to mention another important and useful resource, which is NEEMO, which is a domain ontology dealing with the digital scholarly practice within the humanities, and it's part of the project called NEMIDA, which is a DARIA-affiliated project, and NEEMO is one of the main key outputs of the project. It's an ontology that really follows on from and consolidates similar previous work with the for example, with the AHDS Digital Research Methods Taxonomy and the TADIRA taxonomy. NEEMO is CDOC CRM compliant, and it uses RDFS and Scots rather than OWL, interestingly enough. And you can find the current version at that link there. So let me move over to it. Okay, so in the last few slides, I'm going to focus on something which I personally find interesting, and I started working on with colleagues from my institute, and that's the use of ontologies for studying literary texts. And as I mentioned earlier, we can use ontologies to classify and annotate texts, and these can be any kinds of texts. But we can also use, as I say, this is something that it's kind of fairly new. We can, as far as I'm aware, we can actually classify and annotate text based on different kinds of literary or semantic phenomena, and these can be rhetorical, metrical, narratological. And we could also use ontologies to annotate for intertextuality and relate together different texts across or within traditions. So I'm going to discuss a kind of a series of case studies which help to explain, I think, some of the potential of ontologies in this area. So the first one I'm going to mention is GeoLat, which stands for Geography for Latin Literature, and the aim of the GeoLat is to annotate Latin text for geographical places, events, and persons using ontologies. So with GeoLat, you get a series of Latin texts encoded in TEI, and so then basically they've run a named entity recognition system on these texts in order to extract the relevant words, and then you use the TEI ref attribute to link together the portions of the text with the items, named entities in the text to items in an ontology. And so then, of course, the advantage of this is that the knowledge of in the ontology can be used to enhance the way that users access these texts. So in the case of GeoLat, they've thought in terms of geographical interfaces and creating geographical interfaces which allow you to select an area of interest and then see the text which refer to that particular area. Another case study which I want to talk about is SAWS, which is Sharing Ancient Wisdoms, and the aim of this project or this case study is really the use of ontologies to create enhanced digital editions of nomenological texts, which are collections of wise sayings. And the researchers who were working on this wanted to really focus on intertextuality and to specify the different kinds of relationships between these nomenological texts, such as derivation or allusion, using RDF to create an explicit network to link together different texts. Once again, the texts in question were encoded using TEI, but this time around they used the relation element to actually encode the RDF relations themselves. The SAWS ontology, interestingly enough, uses FRBR UU as an upper ontology, and as I mentioned before, that's actually an ontology that harmonizes C.CRM with the FRBR. So the result of the work that was carried out on these texts was a digital TI edition of these texts, augmented with structured ontological knowledge. And what they were able to do was to create a special interface that allowed users to actually navigate across texts based on the different kinds of relationships. And these relationships basically were kind of semantically typed relationships. So for instance, in the example that I put on a slide, they used the ontological property is variant of, and again, I think it's a very interesting example of what you can do with ontologies and texts, and bringing together the information within the ontology, bringing it to bear on how users access text. Another thing that's I think it's potentially very interesting use of ontologies is in the representation of narratives and storylines. So one project that I'm kind of aware of that focuses on creating semantic characterizations of things like plot or character developments onto media, and that's been applied so far as far as I'm aware to the creation of metadata for describing the content of online amateur fan fiction. Another thing which I think is actually quite interesting, and I mean, the disclaimer here is I've actually worked on this, so I think might actually be kind of something that, in which ontologies are really useful, is as an interlingua to study between the different translations or different variations of a text. So this is something that we worked on at my institute with a researcher from Paris. And the idea really was to model the events in the Odyssey using a narrative ontology, and then to annotate the original Greek text as well as various different French translations of the text using these events and using the protagonists in the ontology. And then see if we couldn't kind of use this ontology to help actually query and to actually help compare these different texts, and to look at how different events are characterized and different characters are actually represented in different translations of the Odyssey. Unfortunately, this work is kind of stalled, but I think that for kind of non-scientific reasons. But I think potentially it could be something that's kind of very, very useful, a kind of a nice way of actually doing work in this area, in this field of traductology. And then finally, I'm going to talk about something I worked on with other colleagues in Italy. It's called Memorato Poetis, and it was an Italian national project which was dedicated to the creation of a computational tool for the comparative analysis of themes, motifs, and figures across different poetic texts. These are mostly epigraphic texts. Belong to a number of different literary traditions, which in this case were the ancient Greek, Latin, Arabic, and Italian poetic traditions. And so we had a corpus which contained poems in each of these languages that had been annotated, mostly on a line-by-line basis, but also sometimes entire poems were annotated, using a tag set of themes and motifs which were taken from the indices used in traditional anthologies of classical poetry. This tag set was organized as a taxonomy, and actually that was very, very useful when it came to actually querying the corpus and finding different texts in terms of the themes and motifs that were present. Unfortunately, the taxonomy was kind of inefficient and wasn't really that well adapted to querying the corpus. So just to give you a little bit of an idea of how it was structured into 6 thematic areas. And so each of these 6 thematic areas were really the top node in a sub-taxonomy, but there were no transversal relations between the nodes in these sub-taxonomies. And there was only really one kind of single relation between the nodes in the taxonomy. What we wanted to do was actually to restructure the taxonomy as an ontology using ontology design principles, such as, for example, ontocline, as I mentioned before. So this is originally it's a diagrammatic representation what the taxonomy looked like. And so, for example, you had one example I can remember particularly well is that under Animalia, you had mors animalium, which I think is death of animals. And then you had a separate tag under homines, which was mors. So basically you had these 2 tags, death of animals and death, which they weren't related together at all. And so I think we kind of realized that this would make querying the corpus very, very unintuitive. So what we did is that we went through the taxonomy, and then we tried to introduce new kinds of relations other than just a kind of general generic taxonomic is our relation to capture different kinds of relationships between concepts. We also used an upper ontology, and in this case Dolce, to give a higher level organization to the tags and then to relate them together so that there weren't these kind of 6 separate taxonomies. There was no relationships between the nodes within each of them. And then we did this work in OWL, and then while we were doing the restructuring, we were working with a domain expert, in this case an expert in Latin poetry, and then with her we developed a series of queries of salient queries, and showed that it was actually much easier, much more intuitive to formulate these queries and then search the corpus using our version of the tags than it had been before. So here you can see a diagrammatic representation of our ontology, and because the original tags were in Latin, so obviously Dolce is in English, so that maybe created a little bit of a problem, but I think overall, I think it was actually quite successful and showed that, ontology engineering does kind of, these principles can have an application also within this area of research. So finally, if I just kind of move on to conclusions, which time have I got? Oh, yeah. So wrapping everything up, what would be the main things that I would want you to take away from my talk? The first thing that is that an acknowledgement that the application of ontologies to this domain is actually still fairly novel, but I think there's a lot more to come. For instance, I think the ongoing popularity of the semantic web is also probably going to feed into the popularity of ontologies in the humanities, and especially the fact that there now exist several important data sets on the semantic web, such as famously Pleiades, but also, and this is something we're working on at my institute, we're trying to actually make available lexical resources, lexicons, the languages like ancient Greek and Latin available on the semantic web as linked open data, and I think these will be useful resources that can be used in work on these languages, on these classical languages. So ontologies, I would say that one of the main advantages of working using ontologies is that they offer us a way of making metadata and annotations more interoperable by relating together categories and tags in terms of what they mean and rendering implicit semantics explicit. And again, it's something that's really based on it's a shared. An ontology should be seen as a shared artifact, something that's actually part of this, derives from the knowledge of a specific community. So ontologies allow us, as I've shown, as I've just shown, they allow us to enrich digital editions of text, and not just text. You can also have maps. You can have different kinds of files by linking them to a semantically structured network of interlinked knowledge resources, which is in this case the linked open data cloud. And we can also use them to represent the structure of text, of story plots, of the different relationships between texts in a way that makes the relevant data sets more queryable as well. But it's important to emphasize really that ontologies make up just one part of a whole emerging ecosystem of tools, resources, standards and technologies, especially those relating to the big kind of infrastructures like Clarin and Daria. And these are really now kind of, this ecosystem is really has become, something that's part of the practice of scholars and technologists in diverse disciplines. But how integral ontologies become to your own particular field or subfield of research is, I think, something still to be established. But I think in certain areas like cultural heritage domain, I think they've shown that they've really shown their worth as part of the kind of practice of researchers in those fields or people working in those fields. So just want to say that, to thank people for these following people for helping me to come up with these slides or for giving me feedback on these slides, and thank you also to Elena for inviting me. Okay, so I'm finished.
Oh, yeah. Sorry, this isn't a question, but I stepped out for a couple of minutes, so I don't know if you mentioned, but actually Daria Teach, one of the first workshops is on creating an ontology.
Oh, I didn't know that.
Yeah, and it's by Panos Konstantopoulos, one of the designers of NEEMO.
Ah, okay.
So it's also there as a resource.
Excellent.
Anything else?
I realize that, especially the logics part was maybe a little bit too dense. I think I maybe packed a lot of information into those slides that maybe...
It has been very useful and very interesting. So, if there's... Pablo?
Hi, Fahad. Thanks for the very interesting talk. I was wondering if there are venues that, that are dedicated to the automatic annotation of ontology terms for literary analysis or that you could think of, conferences that you could point us to,
not that I'm
workshops?
I don't think, not that I'm personally aware of, specifically to the use of ontologies. Not that I'm aware of, no.
Okay.
But it might be interesting to propose such a workshop.
Right, automating different types of annotations. And
Yeah,
via,
that sounds like an interesting topic.
P or whatever.
Yeah.
Thanks.
I had maybe a very basic question. It was just if in Scots it's not possible to add any relation, just related term, and
But there, yeah.
or can you specify more relations, more specific relations?
So in Scots, if you want to...
I mean, like, okay, like at Saurus, or...
So you have
broader, narrower?
Broader, narrow, and then you can say that two concepts are related without specifying how
without
they're related.
specifying.
But if you really want, so for example, if you want to describe different kinds of relations and then give them properties, you really need to use OWL. But you can use OWL Lite, for example, which is, I think,
So
still fairly easy to work with.
if you export, for example, an ontology made with specific relations to Scots, it would lose all that kind of specific information, or...
Yeah, well, if you wanted to convert into purely Scots, you basically would have to, I think you would have to, yeah, you wouldn't be able to, for example, the axioms and so on. I mean, you couldn't say that a property is symmetric. You couldn't say that if you were only using the Scots vocabulary, you couldn't do that.
Okay, thank you. Anything else? So thank you very much for your interesting talk.
Thank you.
Bye. Bye.